it's time now to expand our understanding of bonding by introducing the topic of electronegativity and how it relates to a concept called bond polarity. So before we go any further, this information that I am discussing is found in your Chem 2A textbook in section 6.7 and in your Chem 22 textbook in section 10.8. Let's take a look at what the term electronegativity means. So, definition of electronegativity: the ability of an atom to attract a shared electron pair more closely to its own nucleus. So we know that the nucleus exerts an attractive pull due to its positive charge on the negative electrons. If an atom has greater electronegativity, it's able to kind of pull that shared electron pair and attract it more closely to its own nucleus. Here's the bottom line then. What that means is it turns out that atoms don't share electrons equally. If an atom is more electronegative, or the more electronegative an atom is, the more strongly it attracts an electron pair to its own nucleus, meaning it now has more than its, quote, fair share of electron density. In other words, it's beginning to experience some bit of a nature of an ion in having a partial charge, but not a full charge. So the more electronegative an atom is, the more likely it is to acquire a partial negative charge by pulling those electrons more closely to its own nucleus. The less electronegative an atom is, it's not able to attract the electron pair as strongly. It's more likely to end up without its fair share of electron density and acquire a partial positive charge. It's important to note that electronegativity is in fact another periodic property. So we looked at the periodic property of atomic size, of ionization energy, of metallic character, and electronegativity. It falls right into an understanding of those topics. So if it is a periodic property, that means that you see patterns as you go across a period left to right on the periodic table and as you go down a family top to bottom. Now it's going to be very important for you to look at either figure 6.6 in the 2A text or figure 10.2 in the Chem 22 text to understand what this periodic property of electronegativity looks like. So looking at figure 6.6 or figure 10.2, you can immediately see numerical values of electronegativity that indicate that as you move across a period left to right, electronegativity values are increasing as you go across a period left to right. What that means is that nonmetals can attract a shared electron pair more closely to their nucleus better than metals can. As you go down a family top to bottom, you see that electronegativity values are decreasing. And both of these can be directly related to atomic size issues. As atoms are getting smaller, electrons, valence electrons especially, closer to the nucleus, and it's easier for that atom to exert a greater pull because of its smaller size. As you go down a family top to bottom, atomic size is getting bigger. Valence electrons are farther away from the nucleus, and it's harder for the nucleus to exert as great of a pull on those valence electrons. Now here is a task that seems initially daunting, but in fact is quite easily accomplished in a matter of a couple of minutes. I would like for you to memorize the electronegativity values of all of the period 2 elements, lithium all the way through fluorine. Note that the noble gases are not assigned electronegativity values because they don't engage in bonding situations. They already have the stable electron configuration of an octet, or in helium situation a duet, without having to share or gain or lose electrons. So looking at the values of lithium through fluorine, right, I want you to pay attention here. I've written it down to the electronegativity value of fluorine, which is 4. That is the highest electronegativity that appears on the periodic table. Fluorine is the most electronegative element. And once you memorize that value of 4, you can immediately figure out what all the other period 2 electronegativity values are, because you see there's a pattern. As you move from right to left, you see that you are subtracting 0.5 from each electronegativity. So if you memorize fluorine's electronegativity, then you can immediately figure out what the electronegativities of all of the remaining period 2 elements are by just subtracting 0.5. Some other patterns that are helpful to note is that as you drop down from fluorine to chlorine, the electronegativity decreases by a value of 1. So if I know fluorine is 4, chlorine is 3. That same pattern holds with oxygen and sulfur. Decrease of a value of 1 in electronegativity. Oxygen is 3.5 and sulfur is 2.5. With nitrogen and phosphorus, it's not quite a decrease of 1. It's a decrease of 0.9. Phosphorus has an electronegativity of 2.1, while nitrogen has an electronegativity of 3. But I like to anchor the electronegativity of phosphorus to that of hydrogen. Phosphorus and hydrogen have the same electronegativity values. Both of them are 2.1. So hydrogen, of course, appears over here on the periodic table, but I like to, in my mind, link hydrogen and phosphorus together. Both of them have the same electronegativity values of 2.1. So very quickly, we have figured out a way to remember electronegativities of very, very common elements that we encounter in compounds. Let's take a look at how we can use electronegativity values to understand the type of bond that is present in a molecule. So the molecule that I'm using here as an illustration is HCl. And if we draw the Lewis dot structure of HCl, it's a very easy molecule to draw the dot structure with. Chlorine has 7 valence electrons, hydrogen has 1, for a total of 8 valence electrons. There are only 2 atoms, so we have a bond connecting them, completing the octet for chlorine, and we see right away chlorine has its octet, hydrogen has its duet. Both of these atoms have a stable electron configuration around them, and this is the structure for the HCl molecule. But this is what we want to focus in on now. Exactly what type of bond is existing between the hydrogen and the chlorine? Are they sharing those electrons equally, or is there unequal sharing going on? Well, that's where electronegativity values can help us. So looking over here at the table, chlorine has an electronegativity of 3.0. Hydrogen has an electronegativity of 2.1. And if we look at the difference in electronegativity, so electronegativity difference can be symbolized by this kind of capital italics X. If we look at the difference in electronegativity between hydrogen and chlorine, we come up with an electronegativity value of 0.9. Well, what does that value of 0.9 mean? And in order to understand that, we have to move to this table that explains how the difference in electronegativity between two atoms can be interpreted. Now, I need to state right from the beginning that this table is somewhat arbitrary and can vary slightly from one textbook to another. In fact, the two textbooks that I've referenced here have slightly different cutoff points for these electronegativity differences. I am using a table that I've encountered and seen most frequently in my career teaching chemistry. So here's how we understand this table. If the difference in electronegativity between two atoms falls in the range of 0 to 0.4, we're going to consider that to be a nonpolar covalent bond. What a nonpolar covalent bond means is that there's pretty equal sharing going on between the two atoms, and neither one really has significant partial negative charge or partial positive charge. But what if the electronegativity difference increases above 0.4? If the difference in electronegativity falls in the range of 0.5 to 1.9, now what we're saying is these atoms really do differ significantly in their ability to attract electrons to their nucleus. One of these atoms is really kind of winning in this tug of war for electron density, and that atom probably should be indicated as having a partial negative charge. Not a fully charged ion, but definitely having more than its fair share of electron density. So kind of intermediate on the way to being an ion, but not a full ion. Partial charge. And likewise, the less electronegative atom is kind of losing in this tug of war for electron density, and therefore has a partial positive charge because its nucleus isn't fully surrounded by the complete electron density cloud. So if the electronegativity difference is between 0.5 and 1.9, we're going to call this a polar covalent bond, meaning there is unequal electron sharing going on. Partial negative and partial positive charges exist on atoms. And that is exactly where we find ourselves in the situation with HCl. The electronegativity difference is 0.9. It falls directly in this range of polar covalent bonds. And if I want to more accurately show this picture, I should be putting a partial negative charge on the chlorine and a partial positive charge on the hydrogen, indicating that there is an unequal sharing of electrons going on. I can also represent this unequal sharing of electrons by putting an arrow at the end of the bond pointing towards the more electronegative atom, which is chlorine. It has acquired a partial negative charge because it's pulling those shared electrons more closely to its own nucleus. I should lastly point out what happens if the electronegativity difference is greater than 2. For example, what would happen if fluorine and lithium were to come together in a bonding situation? Well, in that instance, we're right back to what we were talking about when we introduced ionic bonding. Now there's not a sharing of electrons happening. In fact, there is complete electron transfer taking place, and you're forming fully charged ions which are going to hold together due to the electrostatic forces of attraction found in ionic bonding. So this helps us understand why nonmetals and metals react together to form ionic compounds. The difference in electronegativity is so great here that you're not even looking at a sharing of electrons, you're looking at complete electron transfer taking place.